Let x represents the legs of the isosceles right triangle, and y represents the hypotenuse of this right triangle. And we are given that the legs of the isosceles right triangle increases at the rate of 3 meter per second. And in part A, we have to determine the rate at which area changes when one of the legs is 3 meters. So let's see how to do this one. First, I'm going to write down the formula for area, which is given by half times the base times height. The base of this isosceles right triangle is x, and the height of this isosceles right triangle is also x. So we can write down this as a half of x squared. So now we have this equation, area equals half x squared, and this means we can differentiate both sides with respect to time. So let's differentiate both sides with respect to t, and when we do that we get dA over dt, which is the rate at which the area changes, and this equals we put the half and find the derivative of x squared with respect to time. So using the power rule, we write the derivative of x squared is 2x, and then using the chain rule, we differentiate x with respect to time, which is dx over dt. Now let's substitute the values. Before that, we can cancel this 2 and get this simplified. So here we have x times dx over dt. So let's put the value of x, which is 3 meter, and also dx by dt, which represent the rate at which the legs are increasing. So let's put both values and evaluate this. So here it is 3, and dx over dt is also 3. So therefore 3 times 3 equals 9, and the unit is meter square per second. Since this represents the rate at which area, we put this unit as meter square per second. So this is the rate at which the area changes. In part B, we determine the rate at which the area changes when the hypotenuse is 6 meters. So first, let's apply the Pythagorean theorem to this isosceles right triangle. And so it is the sum of the squares of the legs equals the square of the hypotenuse, which is basically the Pythagoras theorem. So therefore we can write this sum of the squares of the legs, that is x squared plus x squared equals the square of the hypotenuse, which is y squared. So x squared plus x squared is 2x squared, and this equals y squared. Now let's replace y equal to 6 here. Therefore, we get y squared, 2x squared equals 6 squared. And so this simplifies to 2x squared equals 6 squared is 36. Dividing both sides by 2, we get x squared equals 18. And we take square root so that we solve for x. So this gives x equal to square root of 18. In fact, this radical can be simplified. That is, we write 18 as a product of two numbers. That is 9 times of 2. And this equals, according to the radical rules, this is square root of 9 times square root of 2. And square root of 9 is 3, and we put this root 2. So here we have x equals 3 root 2. We will utilize this to find the rate of change of area. So I'm going to mark x equals 3 root 2 when y equals 6 meter. This is in fact in meters. Now, as we did in part A, we will find the rate at which the area changes. So let's utilize the area formula of a triangle, which equals half times the base times height. So x times x. So once again, it's going to be half of x squared, and this is area. Let's differentiate both sides with respect to time. So we get dA over dt, and this equals half times the derivative of x squared. First we apply the power rule, so it is 2x times, and then applying the chain rule to differentiate x with respect to time, we get dx over dt. Let's simplify this 2 and this 2 will get cancelled, so we have x times of dx over dt, and we have already determined x equals 3 root 2 when the hypotenuse is 6 meters. So I'm replacing x by 3 root 2 times the dx over dt is 3 meter per second. So we will put 3 here. And so multiplying this, we get 3 times 3 is 9. And this is 9 root 2 meter square per second, because this represents the rate at which the area changing. So 9 root 2 meter square per second is the rate at which area changes when the hypotenuse is 6 meter. In part C, we determine the rate at which the hypotenuse changes. That is, we have to determine dy by dt. So once again, we can apply the Pythagorean theorem to this right triangle. That is, x squared plus x squared equals y squared. Sum of the squares of the legs equals hypotenuse squared. And so this gives 2x squared equals y squared. Now I'm going to use this equation, that is 2x squared equals y squared, and differentiate both sides with respect to time so that we can determine dy by dt. So on the left side we get 2 times of the derivative of x squared is 2x, and applying the chain rule dx over dt, that is the derivative of x. And here we apply the power rule to differentiate y with respect to y squared with respect to time, which is 2y. And then applying the chain rule, we write dy by dt. So let's simplify this. We can divide both sides by 2, and if we do that, this 2 and this 2 will go off. And so this can be written as 2x dx over dt equals y times of dy by dt. Solving for dy by dt, we get dy by dt equals 2x dx by dt divided by y. So let's plug in the values of x, dx by dt, and y. In part B, we have determined that x equals 3 root 2 meters when y equal to 6. Let's plug in that. So this gives 2 times of x is 3 root 2 times dx by dt is 3 meter per second, which is already given. So I plug in 3 divided by y, which equals 6. So let's simplify this. 2 times 3 is 6, and this 6 gets cancelled with this 6. And so finally we are left with 3 times of root 2 in the numerator. So we get 3 root 2. And since this represents hypotenuse, we put the unit as meter per second. And so we see that the rate at which the hypotenuse changing is 3 root 2 meter per second.